This is section 8.2. We're going to have the same cast of characters, things that you're familiar with. We're going to be talking about hypothesis testing. So that means you're going to get a p-value, and you're going to take that p-value, you're going to compare it to a threshold. Okay, so that's what inference means. We're also working with sample means. So we're going to be finding X bar, we're going to be finding the standard deviation, and in this case, we're working with just one sample. So a lot of this is going to feel very familiar. It's stuff that you've seen before. For example, we're talking about two types of sample sizes, large sample sizes and small sample sizes. And when you have a large sample size, you use a z-score. When you have a smaller sample size, you have to use a t-score, which is dependent on your confidence level and something called degrees of freedom. And so if you have 5 items, if you got 5 people in 5 chairs, there are 4 degrees of freedom, one less than the number of items. Why is there 4? Because the first 4 people have the degree of freedom to choose what chair to sit on. The last person has no degree of freedom to select what chair. They take whatever's left over. So if you've got 5 people in a group, the number of degrees of freedom is equal to 4. Why is this important? Because the degrees of freedom changes the shape of the normal distribution for values less than 30. So when you have values in your sample less than 30, the peak of the normal distribution gets distorted, it gets squished down, and the tails get pushed up. That's just what happens to a normal distribution when you have low values for your sample size. That changes the area, it changes our probabilities, and so we have to use a t-distribution for values less than 30. And so now we're going to go in and we're going to do the exact same thing that we've done before. We're going to have a null hypothesis, and it's going to be a mean, it's going to be an average, it's going to be the population current accepted value. And then we are going to challenge that with our alternative hypothesis from a sample, and we are going to select either it's going to be less than the null, greater than the null, or we're not sure if it's greater than, we're not sure if it's less than, but we're pretty sure it's not equal to. So we'll do, both tails for that. And then we're going to establish a threshold, 1%, 5%, or 10% to measure against our p-value. So here's where we calculate our test statistics. Again, you won't be doing this. The spreadsheet will be calculating these for you. And then once you get that p-value, you are going to compare it to the threshold. You compare it to alpha. If your p-value is less than alpha, then that's good for us. That means we get to reject the null hypothesis and replace it with our own. Or if the p-value is greater than alpha, that's bad for us. We foot faulted on the threshold and we fail to reject the null hypothesis. We fail to push the king off the mountain. This was the IQ scores of celebrities. We randomly selected 20 celebrities. So you're thinking, okay, I need to use a t-score for this because this value is less than 30, right? And we want to know, does our sample suggest that celebrity IQs are higher than the average population of 100? So this is our null mean, 100. This is the accepted population IQ score is 100. That's the average IQ score of the entire population. We believe that the IQ of celebrities is higher. So we think that our alternative hypothesis is greater than 100. We think that it's greater than the null. Why greater than? Because this says higher than. It's greater than. So this is important to be able to interpret these vocabulary terms. So if we were to make a quick graph of this, here's our normal distribution. Boop, there we go. We're going to put our mean at 100. I bet you I probably have this graphed on the next page, but we'll do this anyway. And we think that it's higher. And we are looking for the area above the right tail. So what is this p-value? What is that p-value? And how does it compare to the threshold of 5%? Let's go. Let's figure this out. And so here's all of our information. Here is the information from our sample. So here's the mean, here's the standard deviation, here's the degrees of freedom. We crank it in and we get 6.937 as our t-score, as our t-value, the number of standard deviations above the mean our target value is. And so here's the graph that we were talking about. Remember, this is 6.937 standard deviations. So here's your mean at 100. This would be at 100, you'd be 0 standard deviations away from the mean. 1 standard deviation, 2, 3, 4, 5, 6, way over here. And we're looking for this area above this little tiny slice right there. This is a very, very small area, very small. Our p-value is incredibly low. And here's how you punched it into Google Sheets to get this value. And since our p-value is so much lower than the significance value, that is good for us. That means we get to reject the null that celebrities have an IQ close to 100, and we get to replace it with our alternative hypothesis. There's enough evidence to show that famous people have higher IQ than the average IQ of 100. And so you can see from this Google Sheet that you put in the mean and your significance level. You don't need to put in the population standard deviation. Instead, you're just going to use the sample standard deviation because you're doing a sample. You're collecting information from the sample. And then it'll calculate the degrees of freedom, the confidence level, the z-score, and the area above one tail, or if you double it, the area above two tails.